Hi everyone. So now we have defined what derivatives are, and I hope that at this point you can explain exactly what these derivative functions give you. So for example, if you were to plug in certain value of x into this f prime of x, whatever that f prime of x turns out to be, then that value that you get is going to give you the slope of the tangent line to the graph of the original function f of x, right, at that value of x that you use to compute. So in class, I asked you to evaluate or compute the derivative of these functions that you see on the screen using the definition of the derivative, meaning the limit as h goes to 0 of the difference quotient, right? And I think even though we struggled through that computation, we came up with the result for each of these functions. And let me just list what those things turned out to be. So for x squared, f prime of x should have come out to be 2x, and x cubed, this came out to be 3x squared, and for x, this was 1, and for f of x equals 1, this was 0, and for square root of x, I think we got 1 over 2 square root of x. And for f of x equals 1 over x, this turned out to be negative 1 over x squared. So I think that all of you can agree with me that computing the derivative using the definition is very tedious, isn't it? Algebra can get really complex and it takes so long to go through that limit computation. And so what we are about to do in this next step is to come up with different differentiation rules for us to be able to compute these derivatives a lot more efficiently. So we're going to have a bunch of different rules that we're about to study. So make sure that you're practicing each rule as we go over them by doing the homework problem. So the first thing that we're going to learn is what's called the power rule. And so we can actually use the result of what we did in the activity to actually deduce this rule. So what I want to do first is to write all these functions that we differentiated using the power. So meaning that I want to write every single one of these as x to a power. And I think I already had that on the handout that you guys used, but let me just use that. So x squared is already x to a power, so is that. And let me emphasize for this x, this is actually x to the first. And then for 1, we can definitely write this as x to the 0. And square root of x is the same thing as x to the 1/2 using that fractional exponent. And x being in the denominator, I can always write that as x to the negative 1 and so forth. So what I would like to do is to try to come up with the rule of differentiating functions that are of the form x to any power, whether it's going to be some whole number, positive, negative, or even the fraction or any real number. So now comparing these x to a power function to the result of that. Now let me just try to emphasize the fact that 1, you can write this as 1 times x to the 0. And of course 0 is 0 times x to whatever the power. I guess it doesn't really matter what the power is, right? 0 times anything is going to be 0. And rewriting 1 over 2 square root of x, this can be written as 1/2 x to the negative 1/2. And negative 1 over x squared is negative 1 times x to the negative 2. So now that I wrote everything as something times x to a power, I would like you to compare the original power that I had on x and where those numbers appear in the derivative. And I think it's definitely clear that the original x squared, that power 2, now appears as the coefficient on that x. And same thing for x to the third. Now the 3 appears as the coefficient. And it's the same thing with every single one of those exponent that the function had originally. So now if you compare the original exponent on the function to the exponent on the derivative function, I would like you to see the pattern there as well. So the first function, x squared, the power 2, became now x to the first, which I can write as 2 minus 1. So the original exponent minus 1. X cubed function now has 2, which is the same thing as 3 minus 1. And x to the first power, if you look at that 0 there, that is going to be 1 minus 0. So let me skip this down here. Negative 1/2 is, you can get that power by taking the original exponent 1/2, subtracting 1 gives you negative 1/2, and same thing with the negative 2. Negative 1 minus 1, so subtract 1 from the original exponent gives you negative 2. So looking at this, we can deduce the following differentiation rule. So anytime you differentiate something of the form x to some power n. Now remember that n can be any value. And remember this ddx notation. Basically, this is telling us to differentiate this function that's inside the bracket with respect to x, right? That's what this ddx notation is. Now this can be written as, now notice that the original exponent n is going to come down as the coefficient, and the new exponent is going to come from subtracting 1 from the original exponent. So this rule is going to be called the power rule. So using this power rule, let's do a few quick examples. Now again, remember that the power can be anything, right? So let's say that I want to differentiate. So here's the first example. Let's say that I'm going to differentiate. So I'm going to denote this as d dx. And let's differentiate something like x to the 7th. So the derivative of the function x to the 7th, 7 comes down as the coefficient, and the new exponent is going to come from 7 minus 1, so that's going to be x to the 6th. Okay, so example number 2. Let's try differentiating. So again, d dx of the function 5th root of x to the 3rd. Now, remember how you can write this function using the fractional exponent. Index on the radical or the root becomes the denominator, right? So it's going to be x to the 3 still stays in the numerator, but 5 is going to appear in the denominator like that. So the 5th root of x cubed is the same thing as x to the 3/5. But now that I can write this as x to some power using the power rule, 3/5 will come down as the coefficient, and the new exponent on x is going to be 3/5 minus 1. So that's going to be negative 2/5. So let's do just one more example. So example number 3. Say that you want to differentiate 1 over cube root of x. So I just want to quickly review that negative exponent here as well. So again, rewriting this expression as x to some power. If I just rewrite the denominator for now, that's going to be x to the 1/3, right? Because we're taking the cube root. But the fact that that is in the denominator, using the negative exponent, I can write the whole thing as x to the negative 1/3. So here we go. Now we have this x to some power. Using the power rule, again, negative 1/3 comes down as the coefficient. The new exponent on x is going to be negative 1/3 minus 1. So that's negative 1/3 minus 3/3, which gives us negative 4/3. So that would be the derivative of 1 over cube root of x. So make sure that you know this power rule, which is given by this, right? And be able to apply that rule to any function that can be written as x to a power, including these radicals and when the expression happens to be in the denominator, like example number 3.